So now we're going to generalize our separating equilibria into as many partitions as we'd like. We have our unit interval 0 and 1, and then we have 3 intervals, M1, M2, and M3. And we're going to identify those thresholds or those boundaries as X star and X star star. So M1, M2, and M3. Now we have 2 thresholds. We know that Y star, given message 1, is going to be somewhere between 0 and X star over 2 because it is a uniform distribution. Y star given M2 is going to be equal to X star plus X star over 2, and Y given he receives message 3 is going to be equal to X star plus 1 over 2. Now what we have to do is we have to write 2 equations to find X star and X star, where from our past intuition, the patient is indifferent between M1 and M2, and then we also generalize it to being indifferent between M2 and M3 in order to construct X star and X star. So here we go. We're going to assume that there is an indifference point between M1 and M2 at X star, for which we then write X star minus B minus X star over 2 squared equals minus X star minus B minus X star plus X star over 2 whole squared. Same thing holds for the other threshold. Message 1, message 3, minus X star minus B minus X star over 2 equals minus X star minus B minus X star plus 1 over 2. Close brackets, don't move. Squared. Okay. Now we have an equation 1 and we have equation 2. Okay, and we should arrive at a result that is X star over 2 minus B is equal to B minus X star over 2 plus X star over 2. And for the threshold number 2, B plus half minus X star over 2. Well, if we simplify both of the expressions and we put all B's on one side and all X stars on one side, we arrive at 2X star minus X star is equal to 4B, and 2X star minus X star is equal to 4B plus 1. We solve the equations for X star. So the first thing we have to do is multiply equation 1 by 2 and then add 1 and 2. 3X star equal to 12B plus 1. Solving for X star, we find 4B plus 1/3. What this means simply is that we've solved for our optimal first threshold, which is going to be 4b plus 1/3. Right, we have not yet solved for x star star. So now we're going to solve for x star star. This new equation 3, which we have just created. Let me just do it like this. We insert this new equation 3 into 2 and solve for x star star, which allows us to get x star 2 times x star minus 4b minus 1/3 is equal to 4b plus 1. Solving for x star star, we arrive at a solution of 4b plus 2/3. Okay, so now we have 0, 1, x star star. Our x star is 4b plus 1/3, and our x star star is 4b plus 2/3. We have to remember that x star star is by definition less than or equal to 1, which means that 4b plus 2/3 is less than or equal to 1. b is less than or equal to a 12th. A partition that gives us 2 intervals, our b is a 4th. But now that we have 3 intervals, our b is a 12th. When the bias gets smaller, so b equals a 12th, is more restrictive, you can afford to have equilibria with finer and finer divisions. Therefore, bounds on the bias are going to be tighter. Messages must be clearer and more literal. Here we're going full circle back to what we were saying at the very beginning. More equilibria appear as a result, since the patient is becoming more precisely informed by the doctor or the sender of the message. The patient will make fewer mistakes in guessing the real state of the world. Conditional on these 3 messages, then conditional on 2 messages, and even fewer if conditional on 4 messages, then on 3 messages, and so on and so forth. But everything depends on the bias, on the size of the conflict of interest. For small b, separating equilibria will exist. Otherwise, only pooling equilibria hold, these babbling equilibria. Okay, guys, what do you say we start talking about current affairs? For separating equilibria to exist, bias must be relatively small, as we saw. For any meaningful information to be exchanged between, as we put it, between doctor and patient, the doctor wants to move the surgery date, as we said, to the left of the true state of the world in order to maximize his payoff. The doctor always wants to lie downwards. In terms of the pandemic, bias is all over the place, positive and negative, and we can safely assume a babbling equilibrium. This is easily shown by looking at media output and a simple result achieved from employing a loss function of the cheap talk type to the most general, up-to-date data set for the world from the Worldometer site. At optimum, we want 0 deaths, of course, but remember, all our utility function does is minimize the dispersion of data points to arrive at the closest estimate for deaths. The x-axis is the death rate. All the different x's are equal to messages.
The y-axis is the number of total deaths of a biased function of x star, the true death rate, plus biased reporting. The function envisions a rate per 100,000 in population, although the function does not take population numbers into calculation of the death rate itself. Using the cheap talk game, we assume our dependent variable y is total deaths, and x is the death rate for each country, to identify an x star that represents something close to the true state of the world, the real probability a person will die from COVID-19 if infected. X star minimizes the distance between the bias and the true state. Drawing a scatter plot with our course data, we drew a regression line and found a downward concave function which fits our quadratic loss function assumption, the blue line. My own eyeballed estimate, the red line, states that 5 to 10% will die if one tests positive for the virus. The more sophisticated death rate studies vary from 0.12 to 0.2% in the Santa Clara County data to 3.4% with the World Health Organization from March. The model overshot the more complex and detailed statistical analyses. However, in terms of magnitude, the model is not completely off target, given the simplicity of the data analysis. The red line is my interpretation of the patient's optimized loss function. It assumes that as data collection improves, a future data map would have many more data points where, say, Zimbabwe and Bahama sits, as other biases would come into play. The overestimated death rates we have arise from biases mostly for countries which are not testing for the virus, but only report deaths. For example, more recorded deaths for fewer recorded infections due to under-testing, or conversely, a large number of false positive tests. Less systemic failures could contribute to the bias as well. For example, if the virus proliferates within regions of even locations, for example, cruise ships with an elderly population who are more vulnerable to the virus. This interpretation is further supported by an analysis of variance. The patient's objective function is the variance of x. We calculate the variance for every x, make a prediction given our variance, and plot it against the actual reported death toll values. The graph, which you will see in your Excel sheet when you log into Moodle, indicates underreporting in its negative values. Note that the model assumed that the total number of deaths recorded is biased, since many people have died in their homes, care homes, and hospices. Most countries report only total deaths in official statistics. Further aggravating the bias, hospitals do not report corona deaths in time to be recorded, and sometimes even report corona deaths as pneumonia if the virus is identified post-mortem. These are two among several other biases for our Y. Excellent article on bias can be found from the BBC site called The Coronavirus: Why Death and Mortality Rates Differ. Had we chosen a model that sought to predict precisely the death rate and did not take into account an all-encompassing form of bias, we would have looked for proxy data. For example, comparisons between the normal deaths mortality for a given week at a particular time of year and the number of deaths for that same week during the pandemic. With this difference, you can estimate a death rate for coronavirus during that specific week. We would then control for specific biases. This includes those deaths from actual infections and those from people who were unable to be treated, given that the hospitals are overwhelmed with coronavirus.